So some of you have it on Thursday, some of you have it on Friday. We have a 2-week break. Dave will be here, drop-ins every single day. Please don't think that that's a holiday. That's actually you getting ready for the other side, which is going to run 9, 10, 11, 12. There's 4 weeks on the other side, and it gets pretty busy with your other subjects. And you actually want to be getting yourself ready for anything that you are weak at from the first half. Okay? And I'll tell you about the final exam probably next week about the breakup of it. But it has work from all the AE lectures. It has more questions from the B lectures. All right? The final exam has more work from the B lectures than the A lectures, but they're all in there. So that's what it tells you. Public holiday in that week 9. On the Monday, you don't have to come back to uni. So we don't have a lecture, but we have the tutorial. And in that tutorial on the first week back, it says you get quizzed B1. That's today's lecture. So you're not going to get quizzed on today, which is trigonometry, until the other side of the break. Okay, so there's quite a big gap. That's why you might want to make use of the drop-in. You might even actually say, well, I might just come in that second week and see what I can remember about the trigonometry. Anybody want to ask anything about that? Any part of that up there? Otherwise, we are starting on page 81. Anyone want to ask anything? Page 81 otherwise. We ready? Here's what we've got. It says trig functions. So today we're just going back onto trig. You did it in 124. You've gone past this before. It all had degrees in it. Now you get it again, but with radians. Okay, so it's a bit of a revision. So we're about to look at some graphs. We're about to look at some equations, things we looked at before, but now we're in radians. Are you all ready and comfortable? Grab a calculator out if you need one. It's coming up soon. You might want one. Righto. It says, you know that the circumference of a circle, is 2 pi r, okay? So 2 pi r means it goes right round 360 degrees. So 360 degrees is the same as 2 pi r, 2 pi's. So that means 180 degree is 1 pi. Now most people remember this fact because that gets used quite a lot in the conversions. All right, so as you do all these conversions, if this is your first time at converting them, that's the one we tend to remember. That's the one we're going to use. So if we're looking at a 90 degree, all right, a 90 degree, I think of it as half of this particular one. So it'd be a pi on 2. All right, so I think of it as half of a pi, which is going to give you pi on 2. So you better be good at your fractions again, because these all come to you in fractions. So a half of pi is pi on 2, all right? Then what happens is it goes into 1 radian. Radian is the angle subtended at the center of a circle by an arc equal in length to its radius. So they set this so that this particular arc length falls to be exactly the same as the radius. Okay, that's what it's doing. That's what it comes up with. So it says an angle is equal to the length of the arc it subtends on a unit circle when expressed in radians. That's just saying how they came up with it. All right. Now we don't need to remember that part. We need to know how to do the conversions. So down the bottom of page 81, the main thing is you remember that you've got your 180 degrees is equal to pi. And from that you go either way, depending on which way you are starting and where you're going. If you're converting from degrees to radians, what you do is take the number and multiply it by pi on 180. Keep in mind you get fractions, and we want to keep them as fractions. Don't write them as decimals. You'll get marked down. To convert the other way, radians to degrees, now it says multiply by 180 on pi, so it's the opposite. So when you go to set up your resource sheet, make sure it's very clear which one, all right, goes in which way. So it says, or if in terms of pi, just replace the pi with 180. Now I think there's an actual typo in the book. There isn't in the slides, but on the next page where we're about to do the conversions, there's 4 for us to do the first time, and it says convert the following degrees to radians. So these are all degrees, and we have to convert them to radians. So what you want to put up the top of all of these questions, up the top of page 82, on the first group, if we're converting from degrees to radians, we want to multiply by a pi on a 180, so I'm going to put that next to each one of them. So I'm going to put times by pi on 180, times by pi on 180, times by pi on 180 degrees, and pi times 180 degrees. Now I need all those answers simplified. If you're no good at fractions, okay, then make your calculator do it. Just don't put the pi into the calculator. So put the 45 divided by the 180 if you're no good at this, at the fractions. What kind of fraction do you get? I get a pi on 4, which means it's a quarter of pi. All right, so you can do the fraction simplification if you need to on the calculator. Just don't put the pi in. How about a 30 divided by 180? Any ideas? Pi on 6. Remember, these are numbers that are going to be in our life for a while, okay? So you want to remember 30 degrees is a sixth of 180. Therefore, 60 degrees must be a pi on 3, a third of 180 degrees. And again, if you're not good at any fractions, let the calculator do it for you. I think 45 goes into both of these, so 45 goes into this one 4 times, 45 into this one goes 3 times. So I think I've got myself 3 pi on 4. We all okay with that? All those numbers come out as fractions of pi. Okay, fractions of pi. Now, obviously, some don't come out as pretty. So if you got something like 57 degrees, so if you got something like 57 degrees, obviously it's not going to probably work with 180. So let's see what it becomes. I'll put that one, just put it at the end of the row there. If I've got that, and I think that my 57 and my 180, oh, that one does come out to be a fraction. That one comes out to be 1960s. Give me one that won't be a fraction. Which one won't be? Anyone want to take a guess? Go for 19 degrees. Try a 19 degrees. All right. I went with 57 just from the top of my head, but that one's actually going to be a 19 pi on 60. I needed something that was prime. So what's a 19 on 180 give us? Oh, it comes down too, does it? Just stays as it is. So if you had to, this one wouldn't actually simplify. It just stays 19 pi on 180, but you can also come into radians. Remember, you can actually give radians. You can give a decimal. Like this one might be 0.111, okay, radians, 0.11 radians. Sometimes people think that they always have to come with a pi, and they don't, all right? They don't always have to come with a pi. So the second one is the one that has the typo because they've kept the same instruction. So we're supposed to be converting the following. Can you change the words? They're radians to degrees. So the next 4 should have been radians to degrees. Up the top of page 82. Can everyone see it? So here it's been done correctly, but have a look in the actual course reader. It was meant to say radians to degrees. All right, what are you supposed to do for these? For all of these, you're supposed to be multiplying by, this time put 180 on pi. So I'm going to put 180 on pi, 180 on pi. So I'm going to put it next to all of them. 180 on pi. So 1 radian, okay? 1 radian in degrees. Now, when you do this one, you get 180, this time divided by, and you want the pi in there because you need to see what it is. And it's going to come out to be 57, and I'll say to the nearest degree. To the nearest degree. So 1 radian is the same as 57 degrees. So 2.4 radians. Anyone get about 137 or 138 if we go to the nearest degree? We'll go with 138. Just tell me if any of that doesn't agree with you. 138 degrees to the nearest degree. Now you notice this time the next 2 actually came to us with the pi, so that means there's going to be some sort of cancellation. So these might work nicely. That means there won't be a decimal approximation, so it's a 36 degrees. completely. And same with this one here. They will cancel. All right, so check on your own calculators. Make sure you can get all of the same answers. This one comes out to be a 157.5. And I don't round that off because that's a terminating decimal. All right, so you don't ever round off if it's terminating by itself. So there's your conversions, all right? So did everyone fix that typo? This one was going from radians to degrees. Every single one of these has got a degree sign in it. So be careful with your units. Some of you are paying for it in your quizzes. Forgetting your units is quite important. So we do penalise on that. Are you ready for the exact? You've seen these before, except now we've put them in radians. So if you want to put down, same thing as when you did it the first time in 124, okay? This one here, if you want to just note, this one here would be the 30 degrees. This one here would have been the 60 degrees. This one here would have been the 45 degrees. And again, if you want to put that on your resource sheet, there's nothing stopping you. And again, how are you going to memorise it? Again, you don't have to memorise it as such because you've got that resource sheet. We use these little triangles as prompters. Our job is to fill in all of those answers. So do you recall? So a bit of revision. Sine's always opposite over hypotenuse. So fill in all the gaps. I'll start at this end, you start at that end. These ones are the easier ones. I'll get those ones out of the road. You fill in the others. Remember your surd work. Surds are coming back in a small way. You might see the words, give as a rational denominator. Things like that might pop up. Righto, so sine of this one here, pi on 6 is a 1 on 2. Cos of pi on 6 is a root 3 on 2. And the tan is a 1 on root 3. Now again, you're lucky you don't have to memorise it, you get to write them all down, but what I would be upset at is if you had the wrong ones on the resource sheet, which has happened before. Alright, the sine of pi on 3 this time is the root 3 on 1, which you can just write as the root 3 on 2. The cos is 1 on 2, and the tan is the root 3 by itself. All filled in? All right, now you might get asked some of that. Coming up, there's going to be some equation work where we have to rely on those answers. So make sure you've got all of that filled in correctly the first time. Now comes some fun. We've got to do the graphs, okay? And we do a lot more than what we did in the first semester with 124. So here's what's about to happen. It's nice and easy when we've got the apps to draw for us. You know that you all go home and you might know of an app and you test it out, say, can you draw this for me? That's wonderful, but in an exam, our job is going to be to come up with it. So we're about to investigate down the bottom of page 82, and then I'm going to flip it over, okay, and then we're going to do the drawing before I do page 83. So I'm going to investigate how the curves look originally. Here's the first one. The first one says, this is the sine curve. Now, if you want, see down the bottom, you see there it says amplitude and period, okay? So we have to talk about the amplitude and the period quite a bit for all three of these families of curves here. So see the sine curve. It says right now down the bottom of mine, it says that the amplitude is 1 and the period is 2 pi for that particular graph, okay, for that particular graph. Then it says superimposed on it is the cos. And the difference with the cos, and I'll make a point of it because the cos usually starts up high. So make a point to yourself, do a highlighter, perhaps use a highlighter on the curves, but it's the cos curve that starts up high. So I'll put here cos starts here. Now that's not to say all the time, but the most basic curve does, and it's that one we work with. Whereas the sine started at the origin, 0, 0. And then there's about to be a third one superimposed. But the thing about the third one is it's got some asymptotes. And those asymptotes appear because, so you're about to investigate, you're about to find out what the tan looks like. Tan is defined as sine of x divided by cos of x. What can't be the answer in the denominator of any fraction? What can't be? 0. So tan is going to have a problem every time cos is 0. Now cos is my blue graph, so if you look on yours, wherever it is going to be a 0, the cos graph, all right, that means it's 0 there. So there's going to be an asymptote appear here in a minute. Cos is also 0 here. There's going to be an asymptote. Now you've got to keep that in mind because your job is to find those asymptotes on your own. I realise the first one comes drawn for you and I realise you've got apps, but when you're sitting in that test and you've got to call upon, you know, what do I do to find them, find the asymptotes, the idea is you figure out where the problem is. Okay, and the problems occur when the cos of x would have equaled 0. So you'll see that the amplitude and period are the same for sine and cos, and tan throws us out completely because tan's got asymptotes. And if you had to ask yourself what's the amplitude of a tan graph, it is, yeah, it's infinite. Okay, it goes forever. So you'll see that the infinite turns up there, and the period is pi. Now you might want to jot that down next to that graph because that graph has got one of each of them, and they're the most basic ones. So the sine of x is the most basic, the cos of x is the most basic, and the tan of x is the most basic. And what you find underneath is about to inform you about how things can change. So it's about to say, all right, that this is Dave's little opinion because he had this pointed out there. He's just trying to make you remember where and what it is, the highest part of a sine curve. So this was Dave's little, you know, his little throw in there. What to say? Amplitude and period. This is what you've got at the bottom of page 82. So here's the thing that's about to be investigated. Every time you get given a curve, I want you to look at the number in front, which is the constant that it's being multiplied by. That's going to affect your amplitude. So you might want to highlight that the amplitude comes from the number that is at the front of the word. However, that means for both sine and for cos, those two both, that's where you look for your amplitude clue. If that number is a 5, then your amplitude is a 5. If that amplitude is a 7, then it's a 7 for the curve. If it's a -1, it's going to reflect your curve. It's going to mean the amplitude hasn't so much changed, but it's reflected the curve and it's sent it down the bottom, or it's reversed it. However, this guy here is the one that's going to hurt. It's that little number in there next to the x. And that's pointing you to find the period of your curve. So the period of your curve is important because that tells you, when you go to draw it, okay, where you should place your curve. So the calculations happen to be the same if you're a sine or a cos. However, they're slightly different when you're talking about a tan. So the first thing is the amplitude doesn't really apply because the amplitude was infinity anyway. All right, it goes on forever. So it doesn't make a difference if you put a 6 there or a 7 there. It doesn't make a difference to the amplitude. However, this one here is where it hurts because the period for a tan graph starts with a pi, because that's what the original had as its period, a pi, and then you divide it by the number that happens to be sitting in there with the x. Now down the bottom of page 82, it says another way to graph a sine, cos or tan curve is to think of n, which is this number here, so I'll put n is equal to 2 in this case, as being how many cycles are completed in a standard period. So you've got to stop and think, what's a standard period? So underneath, if you want to remind yourself, a standard period for the sine and the cos is 2 pi, and a standard period for the tan is a pi. That's what it sort of tells you above. But if you want to put it in words, all right, a standard period for the sine is a 2 pi. So if that's the case, then this is telling me, all right, so if I had done this for my sine, remember this is a sine, so if I had done the calculation, the period should end up being 2 pi divided by 2, 2 being the number n, okay, it tells you that the period is pi. So there's two ways to think of this. If the period is pi, then I start at 0 and I should complete one complete roller coaster, if you want to think of it like that. One complete roller coaster. So if you start at 0 and go up, by the time you get back to 0, all right, and go up, you're in the same position there to there, it's taken you a period of pi. Or another way of thinking about it is that that n, which was 2 in this case, tells you you should get 2 whole cycles in here, okay? You should get 2 whole cycles in your standard period. So there's two ways to think about it like that. And you need to know how to figure out a period and how to work backwards to figure out the n, because they're about to come. Now what I'm about to do is I'm going to just leave page 83 for a moment, because 83 I find is harder because that's given you the graph and it wants you to come up with a name. So what we're going to do is we're actually going to go and do the drawing first. So on page 84, I'm going to flip through these lectures here, all of these examples here, I'm coming back to them. And then the next thing that appears on page 84 says, if you take your original sine curve, now it's all great for me to draw this with an app, and it's got, here is the original sine curve. Whenever I get asked this in a quiz or an exam, I draw that, I do a dotted line because I want the original, which is what this is asking me for, and then I want you to go and add 1 to everything. How do you want to describe that movement? If you have to add 1 to the whole curve, what's it going to do to your curve? Go with a shift up. So this guy here is telling you to take the curve and move the whole curve up 1. Now if I'm in an exam with a pencil in my hand, I don't have this app in front of me to do it for me, I draw the original and then I also say that the original is about to, instead of being stuck around the 0, having the x-axis as its sort of center, it's about to go up 1. So what I do is I go and find all the main points again, all right, all the main points, and I send everything up by 1. So what I'm about to do is I'm about to join it. I've put those dots there because if you're in an exam, in physical, you know, with you with a pencil, that's what you're going to do. You'll shift the whole base up by 1, and then when you go to draw it, it ends up being put up there. Now, we don't have that in our exams. We have a pencil in our hand and a rubber, an eraser, and our job is to figure out where it goes. So this guy here means it'll be a vertical transformation. So you might want to highlight a vertical transformation is when I see that sort of +1 or -1. A +1 goes up, a -1 goes down. And you saw me put the dots in there because that's what you have to do with your pencil. Physically put those dots and say, this is where I want my new curve to be. Now, there's 3 examples underneath that, but one is incorrect. One shouldn't be in that place. So here's the first. Oh, this one here was an extra one. So Dave just put y equals sine of x minus 3. There's your original. Everything's going to go down by 3. Now that means my scale will need to go down by 3 as well. So when it goes all the way down there, the whole thing just shifts down, all right? So this one here's got an original. It's got a 3, so this isn't still the lecture examples. It says there's 2 things happening here and here. I'm getting louder, so I'm just quietening down so I can talk. Sorry. It's all right. If you want to talk, you're most welcome to out there. So this guy here, the 3, this is going to affect our amplitude. So there's going to be a change in the amplitude, and then there's going to be a shift up. Now, when you're in a test with a pencil in your hand, I tend to, first of all, draw the original. Then I go and do what the 3 has done to it. The 3 has affected it. It's made it go higher. It should end up being up here, and then it should go down here to -3. I would have drawn that curve. And then the last thing I do is add the 1, okay? So this is what happens. First of all right, that's where it goes after you've applied the amplitude change. And now the shift of it is take it all up by 1. Now remember, in a test, you don't have an app that does it for you. So your job is to say, I don't get to the last one until I go through the first, the second, and then I get to the third one. All right? That's the safest way to take it. So these two here, Dave is pointing to where it crosses the x-axis. I'm not going to put that in as much because you actually need your equation work. And we do that after the drawing in the second half of today. So he's about to put two numbers there, all right? And we can solve that later on. If we were asked in a test to put them in, mostly we don't ask you to put those in because they involve a lot more work. So I wouldn't be worried about that for the moment. So this one here, that's the one that he's got, all right? That's the one that he's got he's doing again. I'm not going to do that one yet because what I want to do is get you drawing. I don't want the drawing in front of us first. So this is the one on page 85. So here we go. This is you with a pencil. I say pencil because you can rub it out. If you need an eraser, I'll throw one at you if you need one. But it's the best idea. Or if you need a pencil. Do you need a pencil, anyone? There's a spare one up here. Because you want to make sure that all of these come out right. Okay, so here we go. Your suggestions are handy. So think back to, I'll go and say, think back to page 82, the basic guys. I'm about to write on the side some things before I draw. So you've got some space next to it, maybe on the left-hand side of it. I'm about to ask you, first of all, it's a cos curve. So where should the cos curve start? At the 1. So that's where I'm going to just do that first of all. All right, it should start at the 1. The amplitude has changed. There's a 4, but not only a 4, but there's a minus 4. Now, if it had just been a 4, then I would have moved the dot up here to the positive 4 position. But because it's got a minus 4, what's it telling you? Start down the bottom. So, in fact, this is the first place. So this is where I am about to start. All right? So all those little movements we did, all right, was because the original curve, all right, first of all gets a, it's a cos curve. It then got an amplitude of 4, but then we made it a minus 4, so it reversed itself, all right. So think about what's its period. So again, you might want to get used to writing its period is 2 pi on n, and the n in this case is a 1. So in case you're wondering what it is, it's a 1. So in this case, it should be 2 pi. That means it's supposed to take 2 pi, okay, for it to complete one whole cycle. So by the time I'm at 2 pi, I better be back down here again. Now, if you give yourself some ideas with the dots. So if the lowest happens, so the minus 4 happens, all right, at 2 pi, then the other side of it, the highest happens at this guy up here. So half of it, so the lowest happens, all right, at 2 pi. The highest should happen at the pi. When should it cross over? Half of that again. So it should cross over here. It should cross over here. All right? Can you draw it in as best as you can? So when I say join the dots, it's a cos curve, so you make it come off there, down there, does a turn, goes through there and there. Now again, it's lovely that we've got an app, but can you physically draw that? Have you put the little clues on the side of it? Have you told yourself about the period, and have you told yourself where to start? And why did it start down there? We all good with that? Righto, round 2. Now that gets drawn on top of mine, but I want you to realise that it's about you drawing it with your pencil that's going to be crucial. The one to the right says it's a y equals 3 sine of 2x. So let's start. This is a sine curve. Where does the sine curve start? At the 0. So I've just put a starting dot there. What's the 3 doing for me? The amplitude has now become a 3. So it's not going as high as 3. It's going to go as, it's not going as high as 1. It's going to go as high as 3. And before I think any further, that period, and again, I will put that the period should be 2 pi on my n, and my n in this case is a 2. So a 2 pi divided by 2 tells me that the period is pi. Now on the side, I do my working. I tell myself that the period is pi, so first thing I'll do is put a big fat dot there. I'm supposed to be back to that spot there at pi, by the time I've done one complete cycle. Halfway between those two, all right, I will get my high and, sorry, I'll get my other 0 mark in there. There's my other 0 mark. So there are 3 dots for the zeros. My high happens at pi on 4, all right. So again, I just know that because I halve it and then I halve it again. So that's how you can figure out. It's very symmetrical. So this should be hitting its high up here at 3. This should be hitting its low down here because I halve it. So I find out where it's going to cross, here, here, and here, and then you halve those to find out. If at any point you're unsure, get your calculator, push in a value, and see if it agrees with your diagram. So if I'm not sure whether a pi on 4 should be up here at 3 or at -3, I'll ask my calculator. The only problem with the calculator, it's not a problem, is that it's probably set in your degrees, and if you call out pi on 4, then you probably need to put 45 degrees in. So that's the only thing I'll caution you on. People will get caught with that. Now that's going to be drawn, so I'm about to draw this. I'm about to go up, down, round, and I finish by the time I got to pi. However, we're supposed to draw it for 2 pi's. So it's a matter of draw another one again. So set it up. If you find the setting up nice and easy, do the same thing as before. Give yourself an idea of where the dots want to go. And again, we're not going to be exact, but it's about getting the right markers in there. Have you completed 2 whole cycles by the time you got to the end of 2 pi? That's what you were supposed to do. And the curve gets drawn on top of mine. That's why it looks slightly darker now. All right, the next one says y equals 2 cos of x on 2. So we'll start again. This one's a cos, so where should it start? It's meant to start at 1, but the amplitude has changed. So because the amplitude is now +2, I'll put my dot here and say this is where I'm about to start. I'll go figure out my period from this guy. The period is meant to be 2 pi on n. What's the n value in this case? 1/2. So what is 2 pi divided by 1/2? How are the fraction lovers? What do we get? 4 pi. So it's supposed to take me 4 pi to complete the whole cycle. But I've only asked you for 0 to 2 pi. So I'm only going to get half of this in. Okay? I'm only going to get half of it in. So it was meant to be completed. I'll just show you what it was meant to do. It was meant to be completed from here to here by the time you got to 4 pi. So just on the side, I've given myself an idea. That's what it's meant to do. But we only want the 0 to 2 pi. So how much of that will we get? We're only going to get half, and that means instead of stopping at the high, we're going to be stopping at the low there. So the low should happen at the -2 mark. So again, think about what it was. On the side, I do a quick little sketch. I'm only going to go from high to low. What is half of the 0 to 2 pi? Half of it is right there, so that's where it's going to cross over. So it's a rather elongated, it's a rather slow one, this one. So it's going to go down, cross, and then it's going to go slowly in that direction. Now remember, see my little sketch up here? This little sketch up here says I'm only supposed to go from that high down to that low. I was never meant to get the whole thing in. Let's see what happens when we go through it. All right, it looks like that. All right, so it's about getting those markers, being able to figure out how the amplitude's affecting things and what the period's doing. All right, this one here, where to start? This to me is like I take a diagram and I do a couple of moves with it. It says take the original, which is a sine curve, but make it -1. Now that's affecting the amplitude. So instead of it starting at 1, where is it now starting? -1. So what I'm about to do is I'm about to show you, okay, so it's about to start at -1. It starts not at -1, my apologies. It will go sort of as far as a -1. So it starts at 0, but instead of heading in that direction, okay, I've put a little arrow going like that. Instead of going in that direction, I'm going to dot the minus sign of x so far. So what I'm about to do is go it's meant to get to, the period is the same, so I better just check that you all know the period hasn't changed by 2 pi. So I want to get to there. I want to get to this high, which was the 1 or minus 1. So it's got to get there. So I'm just going to do a bit of a dotted version. So this guy here would be the dotted version. Now what I've drawn there, that dotted version, is just the minus sine of x. So I took a sine of x, I knew where it started, I've done a flip to it, and now what's the big 2 out the front going to tell you? Take the whole curve up. So I'm going to now say shift curve up 2. So what does that mean? So see everything you've drawn there? You've drawn it with your pencil, you've dotted it in. Instead of the x-axis being like the base through which it all goes around, this guy here is going to be like my base. Everything's gone up 2. So where I started at 0, it's gone up 2. Where I had my low here, it's gone up 2. Where I crossed over has gone up 2. Where I hit my high has gone up 2. And then the end of it has gone up 2. Now, remember, you don't have an app. You have your hand and your pencil. So you really do need to think first shift and then the second shift. So this is what's about to happen. It's about to go down. And as best as you can with a pencil and a book in front of you. How can you check that? You can put a number into the calculator. If you want to be sure about it, pick a number. Oh, pick a number. All right. Say, for example, pi. Now, if you pick pi, on your calculator, if you are set in degrees, you want to say not pi, but 180. So if you wanted to say 2 minus the sine of 180, see what happens and see if we've got the right answer in there. Okay? So 2 minus the sine of 180. And it's just easier to do the degrees unless you like shifting from your degrees to radians. It takes a bit of shifting in and out. So are we happy with that shift? Do you get the idea what you need to do? All right. So this is us looking at graphing. Okay. This is us planning how to come up with the graphs. Now I'm about to leave those others. I know there's heaps of them. They even go over the page. All right. But what I want you to do is I'm now going to do what I think is the harder part, which is actually that I'll give you the graph. You come up with the name of it. So you guys go back to page 83, okay? Now you've got an idea of what's been happening there, all right? So this is what happens when I go back to this group, righto, on that one there, no, that one, back to about 13, I think it was. About 13. That one, that one, that one. There it is, page 83. All right, can everyone see it? Now what we've prepared for you, it's nice because on the side it says, you're going to tell me the amplitude now, you're going to figure out the period from the graph, and then you're going to paste it all together in its name. Right? Now I choose to do my drawing first because I think that gives you a better idea of how you got your amplitude and how you got your period. Going back is actually very hard. So, anyone would like to help us out? Amplitude, what can you see from the graph? Amplitude is 1. It seems to go as high as 1 and as low as minus 1. Remember, the x-axis is like its baseline, so it has not been shifted up or down or anything like that. So the amplitude's 1. What about the period? Where can you see the period in the diagram? Where can you see the period? Or another way of asking is, how many complete cycles did it do by the time it got to the end of its standard? Now, do we think this is a sine, cos, or tan? We think it's a sine, so let me just write that up. A sine curve has a period, a normal period, a standard period of 2 pi, which is down here. How many cycles has it completed by the time it got to 2 pi? It got 3 in. So your n is equal to 3. All right, your n is equal to 3. All right, your n is equal to 3. And how are we going to put that into the function part? So this part here, we think it's a sine. We think the amplitude is a 1, so that's the easy part. It's what sits here, all right? It's what sits here. Any suggestions? What should your period be? The period said it was going to be 2 pi, because it was a sine curve, divided by n, which we figured out to be 3. So that n the figuring out of n is very vital to us because it says the period will be 2 pi on 3. Now what's supposed to sit here, normally sits in here, is the sine of n, all right, of nx is what it has. But we've put a theta in there, so I'm going to just say, it should say n theta. So what number will we put in there? A 3, and we'll put a theta in there. Now, from the curve, think back, we got the amplitude because it went up and down 1 from its baseline. We got the period by seeing, well, we could figure n out, right, which is how many complete ones went through. So the period was 2 pi on 3, and what sits in here is just the n value. All right, can you see why they're harder? Round 2, let's start this one, the one underneath it says, look at the curve. Any suggestions on what you think it might be? A sine, a cos, or a tan? A cos. So I've got the idea that this is a cos, and its normal period is 2 pi. So amplitude. Has there been a change in amplitude? What do you think? 2. So it's gone up as high as 2 and down as far as minus 2. So the amplitude is 2. What do you think about the n value? How many has it completed in its standard? So it's gone up to there is 1, then again there's 2, so it's gone through 2. Its period is 2 pi over 2, which is otherwise known as pi. Now you can see that on the graph because by the time it got to pi, it had completed one whole cycle. And what's the function called? Y equals, we want the amplitude, so it goes in there. We want the word cos, so it goes in there. And what I'm waiting for is n theta. So what will we put? 2 theta. Now in this case they were both 2's. All right, so we don't really catch anybody out because you might have put the wrong one in the wrong place. But when we give them the same number, it's hard to catch people out. All right, what do you think about the amplitude of this curve? Sine, cos, or tan? It's a tan curve. The amplitude gets given as? Okay, infinity in both ways. It doesn't have an end. The arrows keep going. Now the thing about a tan curve is that its period is, a standard period, is pi long. Okay, it's pi long. So it says, when you come up with your n value, how many has it completed in a gap of pi? So you have to figure out where's the gap of pi. All right, where is the pi? How many has it completed? Any suggestions? 2. It's completed 2 by the time it gets to pi. So here's the pi. I'll just do a bit of a cut-off there. How many has it completed? So you can see 1 complete. There's a half over there and a half over there. So there's 2 that's been completed. So the period would be pi on 2. That's telling you by the time it got to pi on 2, it actually had completed 1 of its cycle. And the function comes to us as a y. We don't think there's any number out the front. It's hard to tell because even if it had a number out the front, the amplitude hasn't been affected by it. So that's a bit of a, problem there. And then this should say, in there we're waiting for, and again we're waiting for n times theta. So we're going to put 2 theta in there. All right? So we got the idea on those. Now, he also gave us some that were slightly harder on page 84. So I will complete these. I'll do the usual. I'll complete these, but we've got to get to the ones that are on page 84 because that's when he introduced some of the vertical shifts. Okay, some of the vertical shifts. So let me just get to that particular one. So that's the first one you guys have got on page 84. Now, there is a bit of a difference in this, okay, because what happens on this one is it looks as though it's gone, see where it's starting? That's a bit of a giveaway that this guy started at 1 and it didn't come down, but it went up. So it looks like that this has become its baseline there. And if I had to ask you, just imagine the baseline up there now. Have a look at the curve. Do you think it's a sine or a cos curve or a tan curve? Better put that one in. Which one do you think it is? A sine? A sine curve. So we think it's a sine curve. So what do you think has happened? I know that there's this shift of the whole curve. So I know that there's bound to be a +1 at the end of it. But I need the front part of the function. So has the amplitude been affected? Now the amplitude comes when you measure from here to here. That's the amplitude. It's also seen from here to here. Any suggestions on the amplitude? 2. The amplitude is 2. Its period, has it changed? Question is, how many did it complete by the time it got to 2 pi? All right. Now the thing about 2 pi, see the numbers here? These guys here are telling you that this is actually being placed in, it's still in radians, but it's not coming to you as pi on 2 and pi on 4 and pi's and 2 pi's. It's coming to you as a whole radians. So it turns out that the period, the question is, how long did it take to complete one cycle? And the answer is 4. Okay, the answer is 4. And remember, the n value was how many did it complete. So if you want to put the 1 over here, it completed 1. All right. It completed 1. Actually, no, I can't put it completed 1. Hang on a second. We can't have n is 1. We know that there, but what we have to do is, from the information that the period is equal to 2 pi on n, we have to go back and put the 4 in there and solve that for n. All right? So that becomes a little equation. So the ones that don't have the pi's and the pi on 2's and all that, you can see when it completes its cycle. So I know that it's completed one cycle after 4 radians. All right? So it completes it after 4 radians. And it says here, no, I should have left that 4 there, sorry. It says here that n is going to be 2 pi on 4, otherwise known as pi on 2. That's the guy that gets put in over here. So this one should have been a sine curve. I was waiting for n theta, all right? So I need a pi on 2 being multiplied by theta, okay? Oh, it was 2. The 2's out the front because of that. All right, the 2 is out there because of the amplitude, so we'll put that in. That guy has affected there. The period, remember, they become the harder ones for us to pick. But first of all, can you see that the whole curve got shifted up? Okay, that's the first thing, because you might need to start backwards, I guess. See that the curve shifted up. Put that guy back in, that baseline at 1. That gives you that this guy has appeared. This is why there was a shift up. Okay, a shift up. And you know what? At the very end of what you think you have declared, you can always check your answers. Because I believe that if I put 0 in, all right, that I should get the answer 1. I believe that if I put 2 radians in, I should get the answer 1. I believe if I get 1 radian placed in, I should get the answer 3. Now the thing about checking is, if you go to put it on this calculator, you better be in radians. So do you all know how to turn it into radians? Because if you're checking, you can't check while you're in degrees. So again, just small details like that. You can check, but make sure you're in radians. Now it's the next one that shouldn't have been there, because this one here is actually, we're going to have to put just a big cross through it for the moment, because this guy doesn't come until page 86, which is a bit of a horizontal transformation. So he should not have been sitting in there. This one was a horizontal transformation. So if you just write that there, and then put horizontal transformation and put C page 86, all right, C page 86. And then I'll do this one here. which is the bottom of your page 84. So get your head wrapped around one that's a tan. First thing, what do you reckon about the amplitude? All of the tans have an amplitude of infinity, so that's the easy part. Now, period. Again, it's asking, how long does it take for a complete cycle? What can you tell from the diagram? Any suggestions? I want to read that. That's what I want to read. How far is that to that? Because that's the gap that it takes a whole cycle to occur. Any suggestions? It's not quite a 2, but the period is, how long does it take? Pi on 2. It's a half of pi. So the period is a half of pi on 2. All you want to do is say 3 pi on 4, which is 3/4, minus 1/4 pi gives you a half pi. And then what happens with this one? Remember that your job is to figure out. We know it's got something to do with tan. We can't really tell if there's a number there because it would never do much to the diagram as such. Stretch it out a bit more. What has to happen in here is we need to know about, we need to know about the n values. So this one takes me over here. So it's supposed to be that the period, pi on 2, is meant to be the, and back on the other page you get that formula for tan. It looks like n is equal to 2, and I heard somebody call out the 2, but the 2's not the answer to the period. The 2 is needed, but the 2 pops itself back in here, all right? And has anyone noticed any other thing that has happened to this curve? It's gone down one. Because it was not crossing, what happened was this is where its baseline was, and I can tell because of it was supposed to be at the pi on 2 pi's and all that. So this has got a -1. So there's been a -1, and I'll put here shift down. Now they're really hard. They're very, very hard to pick up on all those details. Isn't it negative as well? I think it is. So it has to have a switcheroo on there, so that's the part where the negative happens. So because of where it started, because the tan graph normally goes up, because this one went down first, so I'll put here the clue is down first means minus tan curve. So little clues, there's so much involved, and I think they're the harder ones. I think the graphing ones are easier, all right, than the going backwards one, all right? And the last thing we're going to discuss before we do our break is on page 86, which is the transformation, but this time it's a horizontal transformation. So I'll get to that slide. And this was after all the graphs, and I know I haven't completed them all. We will come in with those. They will actually appear as you go along here. These are still just all the lectures. There they are there. This last one has a horizontal transformation, and these are the hardest of the lot because this one's telling you that you take the original curve and you're either going to slide it left or right. So it all depends on, the first one that's been drawn for you has a plus pi on 2. Now it sounds like it's wrong, but people want that to go to the right. This is actually going to the left. So I need you to highlight this and say, this is going to the left by pi on 2. So what most people do is draw the original, and then make every point move pi to the 2. So where this one was, it's now going over here to this one. Where this one was, it's going over here to this one. Right, and if you shift all your points, if you draw the original and then shift all of them over, so this one's shifted over here, and this one is shifted there. Again, remember, you will have all those dots, and when you join those dots, all right, you get your new curve. Righto? So everything got shifted. And if the question says you have to draw it between 0 and 2 pi, see this last part that has nothing on it? You really should end up going back. Oops, again, sorry, too high. You really should end up going to the 2 pi. All right? And that means you don't really need the first part of the curve. So keep an eye on when it says a given domain as well. So therefore, a left move says plus pi on 2. All right, so he put some extra ones in here. He's put another one. You might just want to, it's not drawn, but you might want to write y equals the sine of x minus pi on 4. That would mean that this was going to be a shift to the left, to the right, to the right. This one is a shift to the right by pi on 4, so you get your original curve, and you shift everything by pi on 4. So again, you get a whole lot of dots. So you start everything off by putting a whole lot of dots, all right, and then you shift it, righto, and it will go over that way, slide across. I think Dave put, that's the lecture example. So again, have a look at what you're wanting. You want a sine curve, so you know where it starts. What's the 4 going to affect? Your amplitude. What is this going to tell you to do? Left or right? It looks like it wants a plus, but it's actually telling you to go left by pi on 2. Now again, you have to produce this graph. So most of us do it in steps, but it's just appeared, all right? It got the original sine curve got affected by the amplitude, and then that's the original one there, and then to move it, okay? That was the, no, that's not the, that, I thought he had 2 on there, sorry. That is the final graph of what it looks like. So the original one, I'll put the original one in. If we had to, the sine curve was there. The original one was sitting like that, and then he shifted that one over to the left by pi on 2. And the last one there for us is a tan. Now this causes a slight hiccup because it's got a different sort of period, and it's also got a +1. It's got a shift as well. So it's got a whole lot of things happening in here. It's a tan curve, all right? So what this is saying is it's got some asymptotes, all right? So you'd have to figure out where the original one is. You wanted it to go up by 1, so it gives it a slight change in its look, all right? That's why it's gone up by 1, so it's as if the line was centered there. And it had also been shifted to the right. So I'll put here, shift up by 1. This one here tells us to shift right by pi on 2. All right? So it takes quite a while to master them. And again, your worksheet and your tutorial is going to get you through that. We're going to have a quick break. We'll go for a 5-minute break because we've got quite a mountain of things. Most of it is just recalling from first semester, but we do want to make sure that we get through all of the info. If you want to go back on any of those curves, just tell me, all right? And we'll do a 5-minute break. So this is nothing new. Everyone in this room has been in the 124 lectures, or should have been, I guess. And you remember that at the point where we say angles of any magnitude, we're now deciding that we've got more than just acute angles. So all of this, nothing new except for now you're thinking in radians. Okay, so the answers to these trig equations must come to us in radians. So here's the first thing. So this is just a refresher. If we want to solve sine of x equals a half, we can rearrange it. What we're asking is, what angle gives us the sine of the angle equals a half? What angle are we looking for? Now, most of us would say there's one answer because our calculator, now remember, when you use your calculator, I don't mind that you're in degrees. Being in radians is a bit awkward because you won't know the decimal numbers for all of those guys. So a pi on 3 won't look like a pi on 3 on that screen. So I would suggest you're probably back in degrees. So make sure you are back in degrees. So it says, if you had to ask your calculator, sine inverse. So this is me doing a sine inverse of a half. I'm asking the calculator, to the best of its knowledge, what angle would make this true? Now the calculator does its best. It supplies me with one answer. But we know there's actually more than one answer. That's what we're talking about. That's what we also talked about in 124. We know the sine curve in front of us, and if you are asked, okay, what angles have a sine of a half, you can clearly see that there are two in this domain, and two keep happening every time you do another cycle. So keep in mind, we've just got the view from 0 to 2 pi in front of us. But if you actually had that curve going continuously from the left and the right, remember these are continuous curves, then you know that there are multiple answers. But we're just fixed in the 0 to 2 pi. Now we can see that there are two spots, and those two spots would be pi on 6, which is what our calculator gave us, the 30 degrees. So that's what this gave us, the 30 degrees. Our job was, how do you find the other one, which is 5 pi on 6. So remember that we used to do, and again, this is all coming back to you. I can hear it coming back to you. All stations 2 central, and your job was to decide. Sine is positive in the first and the second. If you had a 30-degree answer from your calculator, that's the guy in the first quadrant. How do you get the guy in the second quadrant? A little refresher. You never jump off a 90 degree. You always jump off from the 180. So a 180 take away 30 gives you 150, okay? If you go from the 90, you will get a completely different answer. So I'm stressing from 124, you only ever get to a quadrant from the x-axis. You never jump from the y-axis. So this guy here is actually the same as our 150. Now if you think about it, 150 is 5 of those 30s, and that's why a pi on 6 is one answer, and a 5 pi on 6 is the other answer, okay? So that's what we are about to do. We're about to go in search of that. Diagram-wise, the second one just says sine of x equals minus a half, all right? So that means same curve, minus a half shows me that there should be two answers. Because of my all stations 2 central, I know that sine is negative here and here. My calculator, now this is the part where the calculator, I always ask my calculator to do shift, sine. I still make it do just the half because the minus has been worked with. That's why you did this. This is what the minus has told you. All right? If you put the minus a half in there, what does the calculator give you? Calculator gives you a minus 30 degrees, and that can be off-putting. It's a 30 degrees that you want to work with, so I always push shift sine positive a half, and then I decide that the 30 degrees has to be in the third quadrant, so it's going to be coming from there, and the fourth quadrant, it's going to go backwards from there, and that's how you get those two answers. So in case you're wondering, this answer here is a pi, oh dear, this one here is a pi plus a pi on 6, and this one here is a 2 pi minus a pi on 6. Now I'm putting that down because your job is to do the fraction work. How many of you are lovers of fractions? Not many of you. So you're going to find that when you do these equations, it's going to be those little maneuvers that hurt. So this was me saying 180 plus my 30, and this was me saying 360 take away my 30. So just like we did it in 124, we used the degrees. This time we're using radians, and you better love your fractions because they're going to hurt otherwise, okay? And again, this one here just says it's a cos curve. Now I'm just going to keep going through there as long as you realise that you're using your all stations to central. So this is the summary. It's at the bottom of page 87. So it looks quite pretty up here because in the first quadrant everybody's positive. That's the three curves. That's the three curves, and they're all above the x-axis in the first quadrant. In the second quadrant, when you draw the three curves, all right, the only one that is above the x-axis is the sine, and that's why the S is there, and the other two are underneath. That's why the other two are negative in that quadrant. Third quadrant, same as again, you just keep tracking them, all right, and the fourth quadrant. Now that all stations to central is going to prove crucial to you. And do you know what it stands for, and do you know where to jump from? And I say, do you know where to jump from? You can only ever jump from an x-axis. So you jump that way, you jump backwards, you subtract. If you're jumping into this side, you go forwards by adding, and then this side you start at 2 pi and you subtract. So if you need to put that down in that little diagram there, you might want to say to yourself, how do I get into them? I always get into them from the x-axis. Sometimes I'm adding a number, sometimes I'll be subtracting a number. So it's really crucial that you know how to get into quadrants and where angles are. So this is the first one. You'll be amazed at how many people just ignore because they're not really paying attention to the, do you know where this angle is? Because the question's going to be, find the cos of 7 pi on 6, but before you answer the cos of 7 pi on 6, you better find out where 7 pi on 6 is, because your job is to say, is it in, which quadrant is it in, because that's going to decide if I put a plus sign in front of it or a minus sign in front of it. So 7 pi on 6, this is on top of page 88. It just asks you what sign will it be. So it's asking you, in fact, where is it? So where is a 7 pi on 6? If you think about it, this is what you want to draw. You've got your 0. It's gone more than 0. It's gone more than half of pi. It's gone more than 1 pi. Now, I know it's gone more than 1 pi because I know my improper fractions. So my improper fraction, 7 on 6, tells me I'm in here. If you're not sure about whether it's bigger or smaller than that guy there is a 1.5 of pi. Think about it, check it, but he's gone. How much past the pi? Because that's going to come up in a little while, but you might want to put it on there anyway. So at least you know which quadrant it's in, and so therefore you can say that the cos will be negative. And that's going to be a mark for you there. You know that people are going to lose marks because they haven't put a plus or a minus in a spot, depending on the type of question. So it's about finding the angle, okay? So it's going to be negative. So same idea, find the exact value. Exact tells me there's some sort of surge coming, so be warned. Exact value of sine of 7 pi on 6. First problem is, where is 7 pi on 6? And we've just done that. We've decided that it's down here. But when you are down here, it says that only tan is positive. So that means that this should be minus the sine, and then you tell me about how far it jumped in. So you say, I know where it is, I know it's negative the sine of a 7 pi on 6 is how much past the pi? How much did they have to add? They had to add a pi on 6. So in fact this question is minus the sine of pi on 6. And you had answered that back over, and you'll have it on your resource sheet. You answered it back on page 82. What was the sine of pi on 6, otherwise known as the sine of 30 degrees? What do you get? Any suggestions? What do you get for the sine of pi on 6? Negative a half. Negative a half. Now, it said the word exact. I thought, that's why I was thinking it would have been a surd, but it's not actually a surd in that case. He was trying to trick me. probably meant something else to happen. So here's what we've got, okay? That's us having done that question. And ours is there. Now, there are 3 under there. Our job is, first of all, locate it. So in the space to the left of each of the questions, I want you to draw a little axis. I want you to draw a little all stations to central. Where do you think 5 pi on 3 is? So start thinking. This is the 0. It's bigger than that. It's bigger than half a pi. It's bigger than pi. Do I think it's bigger than 3 pi on 2? So that's the problem. Do you think a 1.5 pi compared to a 5 on 3 pi? Just compare. Who comes in and where? What's a 5 on 3 coming in as? 5 divided by 3 is about a 1.6. So who's bigger? This guy here, the 3 pi, or is this guy bigger? Which quadrant are we in? Which one? We're not in the third, we're in the fourth one. And therein lies our problem. This guy here is 3 pi on 2, otherwise known as 1.5, guys. Not that I want to write it like that, but I've written it like that because when you do this on a calculator, a 5 divided by 3 comes up as a 1.6 repeater. Now, all I really need to know is it bigger than 1.5, or is it smaller than 1.5? The answer is it's bigger, so it must be in this quadrant over here. So, first thing is, I figured out that it's positive, so the answer will be the same. It won't be a negative of anything. It'll be the cos of, and your job is to tell me how far back it had jumped. So if this was 2 pi, and we got to 5 pi on 3, the other thing you want to be good at, a 2 pi is also known as a 6 pi on 3. A 6 pi on 3, take away what leaves you a 5 pi on 3? That's the question you want to ask yourselves. So you need to set yourself up. Find where it is, first of all. Decide if it's positive or negative. When you decide, then say who are you related to. That depends on the jump that you have to do. So if you want to call that the gap angle or something like that. And what is the cos of pi on 3? That's the cos of 60 degrees. What's the cos of 60 degrees going to be? A half. So we've got that answer there. So round 2. Start it again. It says the exact value of a tan. So first of all, just underneath the question to the left, I've just put a little grid. Where do you think it is? A 3 pi on 4. So do you think it's gone past there, past there? Do you think it's got to there? Which quadrant should it be in? Is it a whole yet? No. So has it gone past a half? It has. So it must be in this quadrant. So I definitely think it's in this quadrant. In that quadrant, tan is negative. So I've put minus the tan of. Now, that's the gap angle. How far back did you jump? You were at 1 pi if you were on the x-axis. And then when you had to get to 3 pi on 4, you jumped a pi on 4 backwards. So it's about relating, not just where it is, but who it's related to. So it's minus the tan of pi on 4, and then from what you wrote down before, that would be minus, and the tan of 45 is pi on 4? A 1. So the answer is a minus 1. Okay? Yeah? This guy's a half pi, otherwise known as that. This guy is 0.75. Now, I've just put the decimals there just so we can judge. So I think it's bigger than a half, but it's not quite 1. So that lands it in the second quadrant. Even if you have to do the decimals, that's good for considering where it's living. There's one more down the bottom, same sort of idea. Now, when I go to do this, the first thing I did on the left was I put in all stations to central. I realise this is quite big, and I said to you before, this is 0, this is pi. Now, because these are on 6s, I'm going to call my pi a 6 pi on 6. This guy here is a 12 pi on 6, otherwise known as a 2 pi. And when I get around again, this guy will be 18 pi on 6. Now, if you're not sure what I just did, I've gone lapping around, but every time I went past the x-axis, I either called out, I gave it a fraction of 6ths. So I said I started at 0. The next one's normally called pi, but I called it 6 pi on 6. I then went around to the x-axis and said, instead of calling it 2 pi, I called it 12 pi on 6. And then I went around to 18 pi on 6. Now, where do you think 19 pi on 6 lands you? Third quadrant. That's how you can figure it out pretty quickly and efficiently. In the third quadrant, the sign is negative, so it's minus the sine of, and what was the gap that you had jumped from here to here? It was a pi on 6. And again, you're back to what's the sine of pi on 6, which you'll all have on your resource sheet. So the sine of pi on 6 will be, again, it'll be a half. All right. So I better tell Dave to put some questions in there with some of the surds, because all three of those that he picked all had exact values that were lovely rational numbers. So there was no part to worry about there. So have you got the idea of why it is very, very important for you? Because see that guy there, that sign there is going to lose you marks when you're in a test. If you have not identified where it is, then you may miss the fact that it's a negative answer that you should be getting. So again, we've done trig equations before, all right? We did them in 124, we did them with degrees. We're now doing them again but with radians. So it's the same idea. When solving trig equations, we need to make sure to find all possible solutions. Now, we tend to be restricted in a domain, so this domain helps us. If you did extension maths, something a little harder, or perhaps some of the first year maths, you'll find that you don't need to be restricted, and then that there are many, many, many unlimited answers. But we restrict your domain, so your job is to find what we can in our domain, which means there's usually more than one. So this question says, find theta if I tell you that the cos of theta equals a half. Now, we already know that if I go into my calculator and push cos inverse of a half, it gives me the 60 degrees. And the 60 degrees is converted to a pi on 3. Now, I tend to answer in degrees and then I convert mine. You can do what you like, but I find that the easiest because you've probably got all the degrees answers sort of stored in your head. So 60 degrees is a pi on 3. Now, the thing is, the calculator only gives me one answer. So what I should have done at the beginning was identify that the cos is going to be positive when you are in the first and the fourth quadrant. So I won't forget that. The first thing I do is locate where the answers should be. Because if I keep going, I often forget to go back, is what happens. So it says one answer is in the first quadrant. Most people don't get that wrong. It's the finding out of the other one, okay? So that's what we are about to do. Yours says find theta if. Now, it says find theta. It makes you think there's only one answer, but really you've got to say thetas, because there might be more than one. Find theta if sine of theta is, and it says minus. So I've got to first of all establish where is the sign negative in this domain. So first thing that comes up is all stations to central. Where is your sign negative? Sign is negative in the third and the fourth. Now, I usually just put little ticks down there, but you can do what you like. I remind myself that they're in the third and the fourth. Now, by putting that down first, I've made sure that I have actually gone through, I call it a gate. I've gone through the gate that says, hey, when you go to your calculator and it only tells you one thing, make sure you come back and find two answers. One should be in the third quadrant and one should be in the fourth quadrant. Now, that's done its job. So what I go to do now on the calculator, or perhaps you might say from your resource sheet, what you go away and do is say, could you tell the calculator, find out when, or the resource sheet, when is the sine of theta equal to 1 on root 2? Now, I've taken the minus out because it's done its job. So now what angle should I be working with? Now, you can ask your calculator, go shift sine 1 on root 2, or you use your resource sheet, which has got the answers on there. What will it be? 45. Now, I will think in degrees. It comes out first, and then I will think in radians. Now, pi on 4 is great, but guess what? It's not one of the answers, because the two answers I should have should be in the third quadrant and the fourth quadrant. And a pi on 4, 45 degrees, is sitting in the first quadrant. So if you walked away right now, you're not getting most of the marks. So you haven't remembered the crucial part, which is, I need to come back and say there's an answer in the third and an answer in the fourth. The one in the third starts at pi and jumps forward, so it's a pi plus a pi on 4, and the one in the fourth quadrant starts at 2 pi and goes backwards a pi on 4. Now, I write that down because most of us don't get the fractions correct first time. A 1 pi plus a quarter pi, what do you reckon? This has got a common denominator of 4. You make it 4 pi plus 1 pi, which is 5 pi on 4. That's what we're waiting to see. The other one was, again, common denominator of 4. That's an 8 pi. So an 8 pi on 4, an 8 pi on 4 minus 1 pi on 4 gives you 7 pi on 4. And that's how you find the two answers. You notice that pi on 4 is actually not one of the answers given at the bottom because it's not in the third or the fourth quadrant. Okay? What could make life slightly harder? If you turn the page over, and it's already been done for you, but this one here, what makes it slightly harder, is that this has got a 2 theta. So I'm going to run through the thoughts while you've got the working out in front of you. So the first thought I would have, all right, is whereabouts is my answer? Now, before I go anywhere, what I would do is make this cos 2 theta equal to minus a half. So you make sure that the 2 out the front has moved itself over. From that point there, I usually go to my all stations 2 central to say, if cos is negative, I know that it must have been in the second or the third. So I've actually said to myself, when you come out with the answers, they better be in the second and the third quadrants. So that's the first thing I do. I go and ask the calculator, shift cos for a half. All right, I actually don't ask it the minus because the minus has already done its job. And it comes out with a pi on 3, a 60 degrees again. So here's the thing. When it comes up to the setting up, I know it's got something to do with a pi on 3. So the first thing that happens is, when you go to write them down, you've got yourself a pi on 3 in the second quadrant and a pi on 3 in the third quadrant. So the calculator gave us a 60 degrees, which is a pi on 3. We then put the pi on 3 in the second quadrant. We then put the pi on 3 in the third quadrant. That's why we've got these two answers sitting there in front of you. Now what I'd like in that gap is for you to put 2 theta next to it. So it's been left blank. It's allowed to be left blank, but what I think often happens is people don't realise they haven't found theta yet. So they're actually looking at 2 beautiful answers, but those answers are for 2 theta. So here's the problem. Because we're looking at 2 thetas, then our domain must also shift. So what you'll notice is the next thing Dave has written is that the domain had to be multiplied by 2. So where my theta that I'm looking for is between 0 and 2 pi, my 2 thetas are between 0 and 4 pi, which just means that when I come up with these answers, there has to be another 2 next to these. There's got to be another 2. Because these are the first 2 answers on the first lap around, and then I need to go round again for another 2 pi. So there are about to be 2 more answers, and if you're not sure how they got there, this was the one in the second quadrant, and then I gave it a lap around. What do you do when you lap around a whole circle? What do you add on? You add a 360 degrees, which is also known as a 2 pi. So this is the first angle, but added on a 2 pi, and you get an 8 pi on 3. This was the one in the third quadrant, and I want to lap it again. I want to go another whole circle around, so that's a plus a 2 pi. So in case you're wondering where those 2 numbers came from, add that little arrow on there and say, I can see I started with the first 2, but then I had to go round one more time. And now it's ready for you to divide by 2, because this still says 2 theta, and the question had said solve for theta. So you've still got to do a divided by 2. There are 4 answers in this case. So suddenly, where I'm used to getting 2 answers, I'm also now getting 4 answers. All right, so that can make life a little harder. There is one for us to do. Now this one is the third degree of difficulty, which is if someone gives you a sine squared. Now again, you've seen this in first semester, but in case you're concerned, this is really the same as saying sine of theta all squared. But we came up with a way of writing. All mathematicians don't write it like this in red. They write it as sine squared theta. And we know what it means. It means the sine of theta is being squared and it's a 1. Now this is just like a quadratic equation. If x squared was equal to 1, here's the next trap question. How many answers are there to an x squared equals 1? There are 2 answers, and that's often where this one gets tricky, because there should have been a plus or minus 2. In trig land, when I go to do this, there should be 2 answers, plus or minus 1. So you notice that the left-hand side I've taken the square root of it, just like I do with the x's. And on the right-hand side, there are 2 answers waiting. So now the problem is this. This gets split into 2. There are some answers that give sine of theta equal to 1, and then there are some answers that get sine of theta equals minus 1. Now, we need the answers from this side, and we need the answers from that side. Okay? There is no answer to you don't get one angle that has the sign which is plus and minus 1. It doesn't make any sense. So it's just like quadratics. You then split it, so you need an answer from this and an answer from that. This is when you hit your calculator. Now, if you're in degrees, just remember that you're in degrees. Ask it for the shift sine of 1. What do you get for shift sine of 1? Or you might know it. Shift sine of 1 gives you 90 degrees. Now, I'll put the 90 degrees on there, but then I'll say that's a pi on 2. So theta is equal to a pi on 2. Now, it's a boundary angle. So in case you're wondering, why don't I put that in the first and second quadrant and all that? Because it doesn't live in any of the quadrants. When your calculator gives you 30, you know that it has to be then put in a first and a second and a third and a fourth. But if it gives you 90, it's a boundary angle. So a boundary angle means, that it is on one of those axes. So these are the boundary angles. There's a 0, a 90, a 180, a 270, and a 360. So when the calculator says there's just one answer, there really is just one in our domain. What about the sine of theta equals? Now this is the problem. What's it say when you ask it for minus 1? What does your calculator say? Because that's the one you're going to push on the day. Mine says shift sine minus 1. What do you get, Rebecca? I get a minus 90. Now it's not wrong, but that's the way it has been set up. Now, a minus 90 is not in that domain. So let me write, minus 90 is what the calculator gives me, but it's not in that domain. So your job is to say, but a minus 90 is the same as? What is it the same as? Who's on that side down there? Yeah, it's a 270, which is 3 pi on 2. So it's a 270, so I'll put here this is the same as a 270, and it's a 3 pi on 2, as we've got to answer in radians. Righto? Now think about it carefully. Think about your calculator, because if you're in radians, it comes out, it spits out a 3 times a pi times divided by 2, which is 3 3s are 9. 9 divided by 2 is spit out something about the 4.5 ... And that doesn't mean much to you, probably, if you're in radians. So that's why I stay in degrees. Alrighty, so that's us with our trig equations. Most of that happened in 1, 2, 4. So most of that is I've done this before, I've just got to think in radians. We okay with that? The last part we pick up here, and you might have done this a little bit at school, it's just about the arc length. Now, the biggest trap in this is that people don't remember that the definition says theta is in radians. Could you get your highlighter out? Because I'm going to highlight quite often the fact that theta is in radians. So you've got it there on top of page 91. That formula cannot be used. Stop. You cannot enter that formula if your theta has not been prepared. So we like to trap you. You can see some questions at the bottom of 91. And you can see where we're going to trap you. So you really want to say, write the formula down, and on your resource sheet, put a big stop sign and say to yourself, stop if you've got degrees, because you need to convert it. Okay? So that's the main thing. Now the arc length is just telling us, all right, this distance around. This is the arc length. It's a part of the circumference, and that's how it's being calculated. So we get given this formula. This is the arc length if you know the radius and if you know theta, as long as it's in radians. Okay? So here's what we've got. This is just the explanation as to that. Here's what it says. This is your first question. Find the arc length for the following radii and subtended angles. Now, I'm going to do a bit of a tick there, because when I hear that the angle is in radians, I'm allowed to go through with it. So the formula says this. L is equal to R. Sorry about that. It's the way I write that. L is equal to R theta. Theta's been given the tick, so it says you can go ahead and find R is 2 times by theta. Now, theta doesn't have a pi in there, because remember, it can be 1 radian, 1.2 radians, 2 radians. It doesn't have to have a pi next to it. So that is not wrong. It's just saying to you it is 2 radians. So the answer to this comes out to be 4. What are the units? Because you're going to get lots of marks deducted, I'm sure, between Dave and I when we have our discussion. What kind of units will it be in? It's a length, so it'll be in whatever this was in. So if this was in metres, this is still in metres. All right, first trap comes along. What do you see? First thing I do is say there's a stop sign, something like that, because you don't want to get sucked in and put the 60 in there. So the first thing is convert it. So I'll put here, convert to radians. So converting it to radians, again, this is one of those common ones. You know what it is. It's a pi on 3, because it's a third of 180. I give myself the green light, so now I call back that formula. 50 multiplied by a pi on 3. Now, if they want the answer as an exact answer, then I'm going to leave it as 50 pi on 3, and the units I'm in will be millimetres. Now, I probably would not convert that at all. Unless I see Dave or I ask you for 1 decimal place or 2 decimal places or anything like that, significant figures, I would leave it in exact, because that way you get trained to leave it in exact. We good with that one? Next two come up. It says find the arc length. It's just the same as yours there still. I've given myself a tick because I can see these are in radians. So the formula says, all right, that L will equal R theta. So it's a 2 times by a 4 pi on 5. Do the multiplication. It looks like it's an 8 pi on 5. The units that the radius was in will be metres. I'm leaving it as an 8 pi on 5. Give yourself a little stop sign here because that's in degrees. Your job is to convert it. So for you to convert to radians, this was one of the questions earlier on. So it says take the 104 degrees, and I'll just remind you that a pi is a 180 degrees. One of these is a pi on 180. So we're multiplying by a pi on 180. Now I'm just going to see if the 104 divided by the 180 comes down to, anyone else get about a 26 on a 45? Let me look up. Anyone getting a 26 on a 45? Rebecca, is that a yeah? You're my usual checker. That's why I just have to look down. I don't have to look so far up. Just check if the 104 over the 180, I get a 26 on 45. This is now ready to go because it's in radians. So I will say that the length of the arc is r theta. 25 multiplied by a 26 pi on a 45. Now I'm going to let my calculator simplify. I'm going to leave the pi where it is. So all I'm doing is the fraction component. I'm not touching anything else. So I've got myself 130 pi on 9. Now I let my calculator do the fractions for me. I don't bother doing that manually. I let it do the fractions, and then I just take the 130 on 9 and I put the pi back in. Make sure the pi is in the numerator, by the way, not the denominator. The units were centimetres, so centimetres it is. Righto? Unless someone says round it off to significant figures or anything like that, please leave them as exact. All right, so exact is always better. And the last component for us is our area. And again, I want you to highlight on page 92. Highlight that when you go to use this formula, your theta had better be in radians. So again, highlight it because we're again going to try to trap you. I've just stopped because I'm tired of sort of getting louder and louder, guys. Most welcome. It doesn't bother me, but there's other people who are trying to hear. So see the theta, it's in radians. That's where we're bound to try and trick you in our quizzes. So the very first one says find the area of the sector, so it's an area formula. But this guy here is in degrees. Okay, so the problem is that if you want to quote me the half r squared theta, this guy has to be in radians. And it's not. So we have to do a conversion. So put down here that you need to do some sort of converting to it. So a 135, just like before, what did we multiply by to convert it? Now you can leave it like that. You don't have to go and simplify it. You can leave it if you want. Just take the whole thing if you want like that. A 135 pi on a 180. You're most welcome to take it if you want. It then says that the area will be... Yeah. So, I mean, if you let the calculator do it, anyway, I mean, it's either going to get done at some point as half of, again, half of r squared, so it's a 3.6 squared, times by, and this is allowed to go in now because it is actually in radians. When you get your answer, again, I'm going to say leave it in pies, okay, find the answer in an exact. Keep an eye on the units. This was metres, so this answer will be in metres squared. Okay, so it's a half of the 3.6 squared, and I'm going to multiply it by the 3/4. Now, if that gives me 243 on 50, so if anyone else wants to check, 243 pi on 50. Anyone else get that? 243 pi on 50. I'd leave it like that, unless otherwise asked. And then the last little component is not a sector. So if you want to just remind yourself, the word sector, you might want to put it up the top. You can see that a sector is like when you take a piece of the pizza from the center. So this is what a sector looks like. It's taken from the center, and that becomes a sector. Okay? A segment is when someone comes along to the pizza and just slices it off from not the center. So there's the center, and if I come along and take a slice like that, then this becomes a minor segment, and the other side becomes the major segment. So you can think about it. As long as you take a cut and it's got nothing to do with the center, the radius, it hasn't gone near the radius, it can come very close to it, but it hasn't passed through it, you're giving yourself two segments. One is called a minor segment, and the other one's called a major segment. So this is saying to you, this formula says the area of a minor segment. And basically it's a combo of two things. It's a combo of the sector, which is what the first diagram is. Take away the triangle. Now this guy here is when you learnt your cos rule and your sine rule. You also learnt a rule for triangles that didn't have a 90 degree in it, and it went something like half of A times B times the sine of C. That's all they're doing because there's two radiuses there, radii. So that's what they're doing to get that, and that's why they've got the combination. So if you are looking for, remind yourself, this here is called the minor segment, all right? And the formula works, but only if the theta has come to you in radians. So highlight it again, that the theta has to come to you in radians. So the very last one comes up. There's the last page for us to try out. Find the area of the minor segment. So this is a segment, so straight away you will have this on your resource sheet most probably. So you will put that the area for a minor segment is, it's going to be a half r squared theta minus, and then it says a half r squared sine theta. Now you can combine that, my apologies, because I remember it just from scratch rather than the combo, which is that one there, because it's taken out a common factor. So here's the thing, before you walk in, is your theta in radians? There's a check. So I think I'm ready to go. It will be 1/2 times by 2.7 squared multiplied by the 5 pi on 6 minus, then it says the sine of 5 pi on 6. Now, this one here, if you had to, you'd probably just put it in on your calculator, because what's going to happen here is this is still a fraction. What's the sine of 5 pi on 6? So here we go. I've got to investigate where it is. So here it is, all stations 2 central. Whereabouts is 5 pi on 6? First, second, third or fourth? Second quadrant. And to get to the second quadrant, they must have gone back how much? They must have gone back a pi on 6. So this question is really the same as saying, in the brackets, it's waiting for 5 pi on 6, take away the sine of a pi on 6. A pi on 6 is a 30. So what's the sine of 30? What is the sine of 30? Half. So at some point, remember, if you want to push this straight into your calculator, you've got to be cautious, because you either have to be in radians or degrees, or I've just done it without really pushing it in. I am about to push something in, just I'm prepping it first of all, because this answer here is 1/2, so that's what that's become. Now, I will probably leave what that first bit is, 1/2 times 2.7 squared, and the front bit turns out to be, I'll just leave it as a decimal for the moment. This guy at the front is 3.645, and in the answer here, there's some part of a 6th, I'd imagine. So 5 on 6 minus 1/2 gives us about a pi on 3. Gives us about a pi on 3. So if you were doing order of operations, I've just done the brackets first to get a pi on 3. Now that wouldn't always work. Depends on what the value of your sine of, comes out to be. Sometimes it's just an ugly number, and it'll probably just say go to the decimal places. And I'm about to say, what's a third of 3.645? And again, it's come out to 243 on 200. So did anyone else get a 243 pi over a 200? And it's an area, so it's in millimetres squared. Anyone else get the 243 on 200? Again, you wouldn't go to so much effort if Dave or I puts down, round this off to 2 significant figures. I would have plugged it straight in from the very top, but I would have made sure whenever I enter an angle, you better be sure you're in radians or degrees, okay? So be very, very careful of that. Now the second one, okay, is very much the same, so I will probably just end up writing it. See how now it says find the exact area? So this one definitely wants us to go through all that. Yeah, Justin?
The one before.
Yep.
What did you get from 3.645 times 5 and 3 to the answer?
So did we agree to those two numbers, Justin? I just need to check with you. Did you agree with the 3.645?
Yeah.
So, and you agreed with the pi on 3?
Yep.
So all I did was, that's just saying a third of 3.645. It's a third of it.
Okay, so I took 3.645 pi over 3.
And you multiplied by 3?
And no, I took it over by 3. Like, I multiplied it by pi and then over 3.
Oh, okay. You're going to get a decimal answer. Yeah, so you won't actually get a pi, you won't get an exact answer.
Yeah.
So what I tend to do is I tend to go for exact values, because if we always go to the calculator, then what happens on this question is we don't know how to get ourselves out of trouble. Now I'll end up finishing that because we've already done the one before as an exact, and the only other thing I'll say, see the last question? I'll do that one, but see the last question? Dave has put, find the area of the minor segment formed in a centre of a circle of radius 8 centimetres, but he hasn't given us the angle. What he's done is he's given us a chord. So for anyone that wants to try, this is a bit of an extension question. So it's got this question like this. It says there is a radius of 8, there is a radius of 8, and then it says there is a chord. So in case you don't remember what a chord is, it cuts across here. And it says that the chord is 10 centimetres. Now the problem is, I'd love to find the area of that minor segment, which is sitting here on this side, but I don't know the angle. So it's over to you. How would you find the angle in that triangle? So it's over to you. You've got a couple of options. Call some things out. Something from 1 to 4. What lets you find an angle? What lets you find an angle? What kind? Magic, was it? It's called a cos rule. Can you use a cos rule to find an angle? Do you remember your cos rule? So I'll just put here on this little slide, I'll put cos rule to find theta. Because without theta, I can't go ahead and find the area, sorry. So I've given myself the diagram and I've said, yeah, I can sort of see the problem. And remember, there are steps in all of these questions we give you. Establish what it is they gave you and figure out what the question wanted. It wants the area, I can see that, but there's something missing from the question. So therefore, it's a matter of, oh, that means I'm supposed to find theta somehow. Once I find theta, I then go back and do the easy job, which is find the area. Okay, so we can make a question harder by loading it up like that. Okay? Now that gets us to the end, so I'll do some extra notes on here and I'll put them up for you to have a look at if you need them, or if you want to compare them. Keep in mind, A1, A2, A3, A4, A5, A6. That's what your mid-semester is on. If you don't know what week it is, this is week 7 at the moment. Next week is week 8. So you have your tests, your mid-semesters in your tutorials. Come and chat to me if you need some extra bit sorted out.